Good day everyone, I am Grace Gonat Tuftana from BS Ed Math 3. Today I will be going to discuss two following examples. This would be for Calculus 3 under Chapter 6, Application of Integrals. First is example 4 in section 6.3, Volume with rings. So let's start. We're going to determine the volume of the solid obtained by rotating the region bounded by y is equals to 2 square root of x minus 1 and y is equals to x minus 1 about the line x is equals to negative 1. For the solution, as with the previous examples, let's first graph the bounded region and the solid. Now, let's notice that since we're rotating about a vertical axis, and so the cross-sectional area will be a function of y. This also means that we are going to have to rewrite the functions to also get them in terms of y. Y is equals to 2 square root of x minus 1 into x is equals to y raised to the power of 2 over 4 plus 1. Also, y is equals to x minus 1 into x is equals to y plus 1. Here are a couple of sketches of the boundaries of the walls of this object as well as a typical ring. The sketch on the left includes the back portion of the object to give a little context to the figure on the right. The inner and the outer radius for this case is both similar and different from the previous example. This example is similar in the sense that the radii are not just the functions. In this example, the functions are the distances from the y-axis to the edges of the rings. The center of the ring, however, is a distance of 1 from the y-axis. This means that the distance from the center to the edges is a distance from the axis of rotation to the y-axis, or a distance of 1, and then from the y-axis to the edge of the rings. So, the radii are then the functions plus 1, and that is what makes this example different from the previous example. Here we had to add distance to the function value, whereas in the previous example, we needed to subtract the function from this distance. Note that without sketches, that the radii on these problems can be difficult to get. So in summary, we've got the following for the inner and outer radius for this example. For the outer radius, it is equals to y plus 1 is equals to y plus 2. Inner radius is equals to y raised to the power of 2 over 4 plus 1 is equals to y raised to the power of 2 over 4 plus 2. The cross-sectional area is then a times y is equals to pi times y plus 2 raised to the power of 2 minus y raised to the power of 2 over 4 plus 2 raised to the power of 2 is equals to pi times 4y is equals to y raised to the power of 4 over 16. The first ring will occur at y is equals to 0 and the final ring will occur at y is equals to 4, and so these will be our limits of integration. The volume is v is equals to the integral of d and c to a times y d of y is equals to pi and the integral of 4 and 0 to 4y minus y raised to the power of 4 over 16 d of y is equals to pi times 2y raised to the power of 2 minus 1 over 80 y raised to the power of 5 integral of 4 and 0 is equals to 96 pi over 5.